This lecture is going to be about model checking and model selection. We've covered a little bit of this topic in the previous lecture about regression modeling in the real world, but now I'm going to try to explain a few of the different tools and techniques that you can use when you run into specific problems when you're doing your modeling. So model checking and model selection are two areas where there is some debate about the best way to do that, and it's certainly one of the areas in data analysis where it may be more art than science. Certainly, sometimes model checking or selection is not allowed. For example, if you're submitting an analysis to the FDA or to another regulatory agency to get approval, you'll often have to say in advance what are the terms you're going to be using in your model and how it's going to be fit. So you won't be able to actually do model checking or selection when you're trying to answer those specific regulatory questions. It can also lead to some problems. So for example, if you do a lot of model checking and change your model a lot just to tune it to your specific data, you can get something called overfitting, where you fit the model to the data that you have very, very well, but then if you get a new data set, it doesn't fit very well at all. You can also get something like over-testing or a biased inference, where you've performed a lot of different analyses, and at the end of the day, by doing all of those different analyses in advance, you bias the inference that you're going to be doing at the end of the day. In other words, your confidence intervals don't have the coverage that you claim that they do, or that the p-values don't have the properties that you claim that they do. And it might also mean that the estimates that you get are inflated in one direction or the other. But again, you don't want to miss something obvious where you see that there's a particular problem with your data set that somebody else would obviously see. So it's good to do at least a little bit of basic model checking, particularly with exploratory analysis. So just to go over very briefly the basic assumptions for linear regression, in general, you're saying something like the variance is constant. So for each observation that you get, you have a constant variance for the term that represents the error or the stochastic variation. You're summarizing with a linear trend, and you have all the right terms in your model so that there's no sort of bias due to terms being left out, and that there are no big outliers that might drive your analysis in one direction or the other. So I'm going to look at how each of these can sort of change and what you can do to address them. So for example, here I've created a data set where the x values are 100 values equally spaced between 0 and 3, and the y values are just normal values, but they have increasing variance. So as the x value gets bigger, the y value has a bigger variance. So I can fit a linear model, and I can plot those values. Here on the left, I've plotted the y values or the data on the y-axis and the x values on the x-axis. And you can see that the points get more and more variable as you move over here to the right, although the fitted line still seems to go kind of right through the middle of them. You can also then subtract off this fitted line, so you take each point and you subtract this value, and what you get is a cloud of points that are now centered on 0, but again, you can very clearly now see that the variance is increasing over time. You get an increased variance. So if that happens, the confidence intervals and the p-values won't have necessarily their claimed properties if you use the standard estimates that you get from the LM function. So a couple of options of things that you can do. One is you can try to see if you can find another variable that explains the increased variance, and we'll take a look at that in a minute. You can also use something called the vcov-h function to get the variance estimators in the sandwich package. So we looked at that a little bit for Poisson regression. They can also be used for what's called heteroscedastic, which is a really long word for changing variance situation. So here's an example of how you could do that. So again, I've generated this data where the x values are between 0 and 3, and then we have this normal data. And I can fit a linear model and then apply this this function vcov-hc. I actually am missing a library sandwich at the beginning of this. You'll have to load the sandwich library to get this to work. And you can see that you get a variance covariance matrix. So at the end of the day, this term right here is the variance of the intercept estimate, and this term down here is the variance of the estimate for the covariate of interest, here the x variable. And then these are the covariances between the terms which aren't often used in the analysis. And so what you can also do is look at the covariance that you would get if you just used the standard linear model object. And so what you see specifically is that the variance is smaller for both the intercept term, so this number 0.05 is bigger than this number 0.03, as well as for the term for the x variable, in this case the sequence between 0 and 3, and so you see that this number 0.05 is quite a bit bigger than this number here. What does that mean practically? It means that if you use these error estimates that you get out of the regular linear model fit, they will underestimate the amount of variability that you have in your data, and so you'll be more confident in measured associations than you should be. Another thing that you might have to deal with is that if there isn't necessarily a linear trend and you're trying to model it as a linear trend. So in this case, I've created data where the data are normal and the mean is increasing as the cube of the x value. And so if you fit a linear model of these data, you can see that they look kind of curvilinear here. The gray points are curvilinear, and we fit a line through them. So if we subtract off the line, we again see here a set of residuals that are centered at 0, but now you can see this sort of curvy pattern in the residuals. So that's clearly not to be expected. What you expect to see is just like a football-looking cloud or a sort of a round oval-shaped cloud of points over here on the right. So the fact that you have this trend here might lead to some problems in your analysis. So some things that you can do, if you have a sort of a curvilinear trend like the one we saw just there, you could think about using something like Poisson regression if you think it's sort of a multiplicative model. You could use a data transformation like taking the log or some other transformation like the square root. You could smooth the data or fit a nonlinear trend. We're going to talk more about that in next week's prediction lectures. Or you could use linear regression anyway and interpret the linear trend between the two variables as just that. I'm estimating the linear trend between the two variables. I know that there's something else going on here, so I'm going to have to use some other kind of variance covariance estimate to be able to get accurate inference. And you can do this if n is big, and you can still interpret that as the linear trend, even though you won't necessarily get great predictions with that linear model. Another thing that you might look for is if there's a missing covariate. So here again I have data where the variance is increasing with the mean, but variance is increasing from left to right, but I also have a second covariate, the z variable, and the z variable is equal to either minus 0.5 or 0.5, and every other point has a z value of minus 0.5 or 0.5. So the mean is equal to the old mean plus this variation. And so what you can see is that when you fit the linear model and you make the plot here, if you color the points by this z variable, you can see that the blue points tend to be a little bit higher than the green points. And once you take the residuals, you can see that again. And what you could do is if you don't know the z variable, then you can't make this plot very easily. You can't tell that this pattern is here. Although sometimes what you'll see is just a big cloud of points that are below the line or a big cloud of points up here above the line, and that suggests, even if you don't have another measured variable, that there's some other artifact going on in your analysis. In this case, you know that we know what the z variable is, so we can also make a box plot of the residuals. This is a box plot of the residuals by the different values of the variable, and so you can see that the residuals are much lower for the value of z equal to 0.5 then minus 0.5 then it equals 0.5. And so this is a way that you can diagnose whether that variable is playing a role in the analysis that you're going to be doing, is by looking at these sorts of plots colored by the third variable. So first thing that you can do is you can use this exploratory analysis to identify other variables, which you can then include in the model that you're using to relate y to x. You can again use the model agnostic or robust standard error variance estimators if n is big. And in the worst case scenario where you actually haven't measured any other variables that explain the patterns that you're seeing, you can still fit the linear model but just report the pattern that you see, particularly with an added plot in your analysis, to show people that there may be some violation of the assumptions that you're assuming when you're fitting the linear model. So another thing that can cause problems for a linear regression model is when you have outliers. So I've generated x and y variables here that are independent of each other, but you can see that the y values are have some outliers. So for example, there's a couple of values that are very high and one value down here that's very low, while the bulk of the values of y are sort of in the middle here. And so one thing that you can do to try to identify how much influence this outlying point will have on your regression analysis is to first fit the model where you include all of the data points in the model, including this outlier, and get the estimate of the slope of that line. Then delete this point from your data set and refit the line so you'll get a new slope deleting this point. If the two slopes are very different from each other, then this point is having a major impact on the linear regression line. And so if you have these points that are very, very influential, you might want to consider or take more caution when you're interpreting the analysis. If there's a big slope and it's entirely being driven by one point, that might change the interpretation that you have. So what I'm doing here is I'm actually, for every single data point, I'm deleting that point, and I'm taking the difference between the estimated coefficient that we got from the full data set and the estimated coefficient we get, the slope coefficient we get when we leave that data point out of the model. So what you can see is for the outlying points, there's actually quite a bit of difference in the estimates of the slope parameter when you leave those points out. This is particularly true for points that are sort of near the edges, near the boundaries of the data set. So for example, we have a big outlier here that's very, very near the edge of the data set, and it changes the slope estimate dramatically when you take it out of the data set. So you'll notice that that's usually very true. Points near the ends of the data set have a bigger influence, particularly if they're outliers. So what do you do if you have outliers? If they're experimental mistakes and you know that they're a problem or they were a result of somebody collecting the data wrong, you should remove and document the variables that you removed and why you removed them. If they're real variables, so we talked a bit about outliers in income, say, where if you include Bill Gates in the data set, you'll actually have a huge outlier when that's not necessarily an incorrect reporting of that data. You should consider reporting how sensitive your estimate is to the outlier. So for example, you could perform the analysis I did on the previous page where you looked at how the estimate changes as you leave an outlying point out and then report how different those estimates are. Finally, you could consider using a robust linear model fit with something like the RLM function that's in the MAS package. So RLM is just robust linear models. And what that's going to do is it's basically going to fit the data where you downweight points that are likely to be outliers. So here I've again generated that same data set with outliers, and I fit both the linear model and the robust linear model. And so it's the exact same syntax for both models. And then I can look at the coefficients that I get from the linear model, which seem to be fairly large for both the intercept term and for the slope term. Then if I look at the robust linear model, both the intercept and the slope are very much lower. This makes a little bit more sense because y and x are generated as totally independent of each other, so there really shouldn't be a very large x coefficient. Another way to look at that is to actually look at the fitted data. So here again is the data set, the x values on the x-axis and the y values on the y-axis, with the outliers being very large values. And then you can see two lines. The blue line is the line you get from LM, and the green line you get is from the robust linear model. When you're zoomed out this far, it's kind of hard to see the difference between the two lines. But if you zoom in, what you see is that the linear model is actually estimating that there's a slope here, and that's because it's being dragged down by these outlying points. Whereas the robust linear model is downweighting those points and it's fitting something closer to 0, which is what should be fit because these two variables are independent of each other. So you can use robust linear modeling if you see that you have a lot of outliers and you might want to be able to take them into account. So I've made a lot of different kinds of plots in this model checking, and it turns out that a lot of them are automated for you. So for example, if you generate these data and fit a linear model object, if you just say plot the linear model object, it'll show you a set of points. So for example, it'll show you the fitted values versus the residuals, where you can look for differences in variation between the two things. Difference in variation. So if the fitted values increase, you get an increase in the residual variation. Then you know you might be looking at something that's more like count data, or you might be seeing an outlying value. It also labels points that might be of potential interest in terms of outliers. It makes a QQ plot. So we talked about QQ plots earlier in the class. It's a quantile plot. So on the x-axis is the quantiles of the normal 0, 1 distribution. And on the y-axis is the standardized residuals. So these are residuals that are standardized so that they should look like a normal 0, 1 if all the model assumptions hold true. And so what you can see here, for example, is most of these points lie right along this line, which is what you'd expect. If you saw a big deviation from the dotted 45-degree line, you might expect that your normal assumption might be violated by the data that you're looking at. So another thing that you might look at for model checking is something called the deviance. I'm again not going to go into too many details here. This is actually something that's, if you're interested in the mathematics or the statistics behind generalized linear models, you can go and look at the deviance. It's a commonly reported measure that tells you something about your model fit. It usually compares the model where every point gets its own parameter. This is called the saturated model. And so what it is it's a model that perfectly fits the data, and you compare that to the model that you're using and see if your model still explains most of the variation in the data, even using a much smaller number of parameters. On its own, it doesn't tell you what's wrong. In other words, the deviance is just a number. It doesn't tell you in what way your model is wrong. It just might tell you that your model is wrong. And in particular, you might have a model that's okay. In other words, it's conservative. You get okay statistical inference in the sense that you don't get a lot of false positives. In that case, you might still get a very large deviance because the deviance is measuring the difference from the perfect model, the model where there's a parameter for every data point. Another thing to keep in mind is if you're going to be using deviances is you can't compare deviances for models with different sample sizes. Again, this is an area that if you look up a lot of information on Wikipedia or other places, or looking at any sort of standard generalized linear models textbook, you can learn a lot more about it, but we won't be talking too much more about that in the class. Something to keep in mind is a lot of people use R squared to summarize linear model fits, and it may not necessarily be the best summary. So this is again from the Wikipedia article on that I referenced earlier when I was talking about R squared in regression in the real world. And so what you can see is that these linear regressions all have the same R squared, but you can see that they fit the data dramatically differently in each case. So in this case, it's sort of a reasonable fit to the center of the distribution. In this case, you see a curvy set of data points which are not fit by the line well at all. In this case, you see sort of all the points at one place and then another point at a different value of x. In all of these different cases, you get dramatically different interpretations of what that linear regression line means, but they all have the same R squared value. The key take-home message here is that any number that you choose to summarize how well that the model fits, if it's just one number, it's not necessarily going to tell the whole story. So including lines that show fitted values and plots that show diagnostics are incredibly useful for evaluating model fits. The last thing I'm going to talk about in this section is model selection. So in many cases, you have more variables than you want to be able to include in your model, so you have to do some sort of filtering. And there's a couple of different ways that you can do that filtering. So the best way is to have domain-specific knowledge. So if you know something about which variables should be included in the model based on your previous experience, and you know which models should, or which variables can definitely be excluded, you should use that as much as possible. You can also use exploratory analysis by making plots and by making plots of residuals and coloring them by different variables to try to identify if there are variables that you missed in your model and that you might want to include. And finally, you can use statistical selection. So I'm going to talk a little bit about different strategies for statistical selection or automated selection of variables to include in your model. This is an area of ongoing research in statistics, and it's also an area that can inspire some controversy, because if you do a statistical model selection first, then the inference that you're going to get from your model may be biased, because you're actually using the data to pick the variables and then reusing the data again to try to perform a statistical inference, which doesn't necessarily always work. So there's a lot of different options. Stepwise is a particular strategy of putting in one additional term at a time or subtracting one term at a time. AIC and BIC are different ways of determining what is a good model, and in particular, it's important to take into account the fact that including additional terms means that you're including additional parameters that you're fitting in your data set, and you want to be penalized if you include a lot of different parameters. Even though you'll fit the data well, you're using a lot of data to fit the data well. There's also more modern approaches like lasso, ridge regression, and all that sort of thing, which I'm not going to go into too much detail here in this class as well, but there's some references for future reading at the end of this talk. So again, statistical selection may bias your inference. One way to avoid this to some extent is to perform the variable selection on a subset of your data set. So take some of the observations and do variable selection, and then do a second set of variables and do model inference. That is useful, especially if you have a very large sample size, but may be less useful if you don't have very many data points. So an important thing to know is that when you're choosing how to determine what is a good model, R-squared alone isn't enough, both for the reasons of the plots I showed you previously, but also because R-squared always will get bigger if you include more covariates or more variables in your model. So that might not necessarily be good because it might not improve very much. You might not want to include a term that only improves R-squared a little bit, but is one more parameter that you have to estimate. Adjusted R-squared is a little better. It's the R-squared term taking into account the number of estimated parameters. So if you include new terms in the model, new covariates in the model, and they improve R-squared only a little bit, you get penalized for including too many terms that don't have a big improvement in R-squared. AIC and BIC are what are called information criteria, and they also do similar sorts of things where they try to penalize models that have more parameters. So I'm going to show you an example of how these work with the movie data, and then we'll talk a little bit about caveats. So again, this is the data on movies where we have the Rotten Tomatoes score, their rating, and their genre, and their box office, and their running time. And so one thing that we might want to do is actually do model selection, where we actually say, okay, we want to model the score, the Rotten Tomatoes score, but we don't know what variables to include in the model. And so one way that you can do that is with the step function in R. So you can fit a linear model where you tell the linear model which data set to use, in this case the movies data set, and you say that you're going to start off with a very specific model which is including all of the terms in the that are included in this data set. So in this case, that's the rating, the genre, the box office, and the running time. And then what this procedure will do is it will go through and it will consider deleting one of the variables. And then once it does, it'll recompute this score, this AIC score, and see if it got better or worse. If it got better, then it will try again. It will either try to delete a term or it will try to add a term back in. There's three different ways that this step function can work. It can either be forward selection. In that case, it starts with the model with no variables in the model and just considers adding one at a time. It can be backward. That's where you start with the model that has all of the terms, and then it only works backward. It only deletes terms from the model. Or it can be both, and that is where it either adds or deletes terms as at each step of the model. At the end of the day, it chooses a particular cutoff where the AIC isn't changing, the score isn't changing very much, and it returns for you a model that is fit for the data. So in this case, what it says is it performs this procedure, and at the end of the day, it only includes the terms box office and running time in the model. And it gives you estimates for the coefficients for those terms, but remember those coefficients might be slightly biased by the fact that you did a selection step first. Another one that you can do is you can use the Leaps package in R. So you can type library Leaps after you've installed it. And what you can do is you can actually apply the function reg subsets to the data set. And so what that'll do is it'll actually look at all possible subsets of variables and it'll calculate the BIC score. And so what you can see then is for each of the different models that it fits, it can tell you the BIC score, and it can tell you which of the different terms were included in the model. So a square indicating that this model includes these different terms in the model, and it gives you the BIC for the model, where the goal is to try to minimize the BIC. So another one that you can use to calculate the BIC is the bic.glm function in the BMA package. So again, I'm going to use bic.glm. I'm going to tell it that the family is Gaussian. You might actually be able to use this with Poisson or binomial families as well for Poisson or logistic regression. You tell it where the data is coming from, again, this movies data set, and we're going to start off with the model that includes all of the terms in the model. So on the left-hand side is the score variable, then tilde, and then dot, which says includes all the other variables as possible covariates. And so what this does is it actually does a kind of model averaging, and what it does is it actually calculates the posterior probabilities that each of the terms should be included in the model. So for example, this is the posterior probability that the rating term should be included in the model. It's 0, so it probably shouldn't be included, whereas genre and box office should definitely be included in the model, and running time isn't necessarily that much more informative. It also gives you posterior estimates of the coefficients. These are slightly corrected from the coefficients that you would get if you just fit the model directly, and so that allows for at least a little bit of understanding that you've done some selection before you're doing your inference. So some notes and further resources. First, exploratory and visual analysis is absolutely key here. So even if you're going to do some kind of statistical model selection or statistical model checking, it's very important to do exploratory analyses because you can often see in visual plots what you definitely can't see in just one-dimensional summaries or one-dimensional statistics of the data. Automatic selection will give you an answer, but it may bias your inference, and it definitely could overfit in the sense that it might fit your data set very, very well, but the next data set that comes along, it might not fit. So you might think about separating your sample into two groups and using one group to estimate the selection step, and another approach to do, or another set of the subset of the data to do the inference. The goal here is not necessarily to get the causal model. So despite getting a specific model that's been calculated by an automated procedure, it's not necessarily the causal model. In other words, it might not necessarily be the exact correct model that should be used. It's just one estimate of a possible model that you could use. I've linked here to the LARS package, which does some more advanced feature selection for sort of high-dimensional models like the Lasso. And then the Elements of Machine Learning book actually has quite a bit on model selection and choosing variables to include in models. And it's very good and a good reference to check out.